D2L. So we're working on law of sines, just a couple more applications here. A woman in a hot air balloon is directly above a straight road 1.5 miles long that joins 2 villages. She finds that the town closer to her is at an angle of depression of 35 degrees, and the farther one is at an angle of depression of 31 degrees. How high above the ground is the balloon? We'll round our answer to the nearest hundredth. Oh, we definitely need a good diagram here. So we've got 2 villages that are 1.5 miles apart. There's a lady in a balloon above it. Now, it doesn't say anything about how, like, she's dead center between the two roads. It just says she's directly above this. So, you know, she could be over here. And we know that she's not in the center because we got 2 different angles of depression. All right. The town that she is closer to, so this one here, her angle of depression is 35. So remember, angle of depression, if you're looking straight, it's the amount that you're looking down. So this is 35 degrees, but because the ground is flat and this is perfectly horizontal, we have 2 parallel lines cut by this blue transversal, and alternate interior angles are congruent, so that makes this angle down here 35 as well. And then the angle of depression to the other town is 31 degrees. I'm not going to do all that. I'm just going to throw the 31 down here. All right. We want to know how high above the ground the balloon is. So we're looking for this distance right here. And the height is always a perfectly vertical line, so that's creating right angles. And we're trying to find this height here. Well, I just made 2 right triangles. Do you think we're going to end up using law of sines?
Probably not.
Probably not. What do we use when we have right triangles? We just use SOHCAHTOA. So chances are I'm just going to be using SOHCAHTOA here, but I got to figure out how to get this height. Anybody have any ideas? Like big plan ideas, not specific ideas, but big plan ideas. I'll notice that we have this triangle. And then we have this triangle. Both right triangles. And they both share a side H. If we could figure out some kind of expression, because the problem is we're not getting an exact answer because we don't know exactly how long this distance is or exactly how long this distance is. Now we could write those bottoms as algebraic expressions. I could call this one x, and the other one, since the entire distance is 1.5, we could call this one 1.5 minus x. What we can do is write variable expressions that represent the height of each of these 2 triangles and solve for x. That would give us the bottom, and then we can find the height. So I'm going to start with the yellow triangle first. The height is opposite, the bottom side is adjacent, so we could say that tangent of 35 is equal to h over x. it would follow then that h is equal to x times tangent of 35. I just multiplied both sides by x. We look at our green triangle. Again, we're dealing with the height is the opposite side and the bottom is our adjacent side, so that's tangent. Tangent of 31 degrees is equal to h over 1.5 minus x. And I can multiply both sides by this denominator, and that's going to give us h is equal to 1.5 minus x times tangent of 31. Any questions on anything I've done so far?
Is this kind of circling back because this seems familiar as in first week, couple weeks?
Yeah, we're just using SOHCAHTOA here, which is what we were doing at the beginning. So sometimes, you see, the reason it falls into this section is because if you look at the big triangle, this is an oblique triangle. So that's why it's falling into the oblique triangle category. But during our solving process, we might end up reverting back to SOHCAHTOA if we develop right triangles, which is what ended up happening for us.
Oh, okay. So it's kind of like tucking into itself. Like it's still somewhat new material, but it's just like incorporating like the fundamentals from the beginning.
Exactly.
Okay.
You know how that is with math. We always have to reach back to something that we've learned previously to apply it to something new that happens frequently. So yes, you're exactly right. All right, I got h equaling two different things. H equals this and h equals that. Well, if h equals both of those things, those two things have to be equal to each other. That's our transitive property of equality. So we're going to set x times tangent of 35 equal to 1.5 minus x times tangent of 31. And we want to solve for x. The reason we want to solve for x is because if I solve for x, I have the bottom of this yellow triangle over here, and I'll be able to easily get the height. In fact, to get the height, I could just, I hate that I can't point circle. All right, I could just plug it right into that equation and get the height. I don't even have to go back to my diagram. All right, I got two x's. Got one here and I got one here. Well, the one is accessible, one on the left, but the one on the right is trapped inside those parentheses. So we're going to have to get rid of the parentheses by distributing. Still have two x's, both linear, so we're going to use that technique where we get all the terms containing an x on one side, all the terms that don't have an x on the opposite side, factor out the x. Now it'll show just once and divide to get a final answer. So move this turn the right over. We have a common factor of x on the left now that we can factor. And then x will divide both sides by this big thing here in parentheses.
Hey, Allison, your sound keeps like, I don't know, there's something wrong with it. It's like buzzing.
All right, let me get a headset. It kind of keeps freaking out a bit.
Can anyone else hear her?
Is that better?
Yes, that's better.
Now,
Now it's not better for you, Alex?
no, it's doing good now.
Okay. All right, so now we have to put this in our calculator. Make sure when you put it in your calculator that you have this denominator in parentheses. You know, honestly, in a effort of having the most accurate answer, if this thing right here is equal to x, and the way that we're going to find the height is by substituting that in for this, the most accurate answer, you would keep that crazy fraction I have boxed at the bottom and then multiply it by tangent of 35. That would give us the most accurate answer. If you're really not comfortable with that, you can find the x and then multiply it by the tangent of 35. So if someone wants to pop that in their calculator, let me know, and we'll have our h value.
I think I got the answer.
Your final answer, the height?
No, the x value.
Okay, what'd you get for your x value?
9.072.
That is not what I have written in my notes. Are you in degree mode?
Yes.
Did you put parentheses around the denominator?
Yeah. Well, let me try something.
Did anybody else get an x?
I did minus instead of plus.
There you go.
There we go.
So did you get 0.69 instead?
Yeah, 0.6927 or something like that.
Okay, that's even better. And then to get the height, we're just plugging that into our one height formula. You could plug it into either. It's just the top one looked easier. And we'll get our height. Rounded to the nearest hundredth. Anybody get an answer? It won't be something very big because we're in the unit of miles. Anybody with an answer?
Should I just do my answer?
Sure, if you have one.
0.485.
So it's 8.5. We're rounding to the nearest hundredth, so we'll make that
0.49.
49.
Yeah.
And our unit is miles. Questions, anybody? The last topic in this section is finding the area of a triangle given a side, an angle, and a side. We're going to learn a couple new formulas for area of a triangle. I mean, so far we know that area equals 1/2 base times height, and really that is the key one, and we're building off of that. But sometimes they don't give us the height. Like here, if they're giving us some kind of not right triangle, they're not telling us what the height is. They're giving us a side, an angle, and a side. So we know this. They're giving us a side, an angle B, and then another side. We don't know the height of the triangle. So really what we're doing to derive this formula is if I drop a perpendicular down here, if I could figure out the height, that would be great. Well, I should be able to find the height using SOHCAHTOA because this angle is known and this side is known. So the height is opposite, side C is our hypotenuse, so that's sine of angle B would be equal to H over C. The height then, we could solve for H. We're going to get that the height is equal to C times sine of B. Our regular area formula is 1/2 the base times the height. Well, our base is given to us, that's side B, and our height is now this down here. So our formula morphs into A equals 1/2 B C times sine of B. And that's, oh yeah, that's our very, oh, I labeled my sides wrong. Silly me. This bottom one's A because it's across from angle A. Sorry. Okay, so our base is A, not C, or not B. Man, that messed up my moment. All right, so, and there's that formula right there. So basically, it is just our 1/2 base times height formula. It's just they don't explicitly give us the height, so we have to use SOHCAHTOA to get the height. And the only reason we have 3 formulas is because depending on which angle I started with, my opposite side is different. So I end up with these 3 formulas. I try to remember it as just one though. It's 1/2 2 of the side times 2 of the sides times sine of the third angle. Right? We don't want, no variable is used more than once. All right, so let's find the area of the triangle around our answer to the nearest hundredth. The area is going to be 1/2. I'm going to multiply the 2 sides together. And then it's going to be sine of the third angle. And I say the third angle because I mean like the third side would be C, and then it's angle C. And then we just put it in our calculator. Rounding to the nearest hundredth, we end up with 163.24. And our unit is going to be square kilometers. We're squaring it because it's area. Questions at all? Okay, let's take it to an application then. A real estate agent wants to find the area of a triangular lot. A surveyor takes measurements and finds that 2 sides are 52.1 meters and 21.3 meters, and the angle between them is 42.2 degrees. What is the area of the triangular lot? I'd probably draw a picture even though I don't really need it. Area is going to be 1/2 the 2 sides multiplied together times sine of the angle in between them. We'll round to the nearest hundredth again. 372.71 squared.
How do you decide it's going to be a sine?
Because it's always sine. Because if I were to drop this perpendicular, making a right angle here, and I'm trying to find the height from this angle here, that's opposite. Right? Cosine is adjacent over hypotenuse. So since I'm trying to find this height here, and from the angle I know it's opposite, and I have the hypotenuse, we're going to use sine. Does that answer your question, Jordan?
Yeah. Thank you.
Anybody else? All right, so on to the ambiguous case of law of sines. The ambiguous case of law of sines comes up if we're given the lengths of two sides and the angle opposite one of the sides. So this is our side-side angle that there's no congruence axiom for. When this happens, it's possible that 0, 1, or 2 triangles can exist. So let's take a look at a little picture here. Suppose we know the measure of an acute angle A of triangle ABC. So B is over here somewhere. And we also know the length of side B, so it's opposite this like floating angle, and the length of side A, which is this one over here. Don't know how big this one is. So we have to draw the side of length A opposite angle A. So I feel like there's a whole lot of hoopla here, and then I'm going to tell you how to make your life a whole lot easier. Yeah, we are using all these rules, but I'm not going to go through all these steps every single time I do one of these problems. So the key to determining the number of possible triangles, if any, lies primarily with the height of the triangle and the fact that the height is equal to B times sine of A. Right, because if this is angle A here, sine of angle A is equal to opposite over hypotenuse, and then I can solve H and I get this B sine of A, just like we did with the area problems. All right. If the height is longer than this the second side that we know that we have to draw in, then no triangle exists. See, the height is the shortest distance from angle C down to the other side, a straight line. So that's the shortest that our side can possibly be, and it actually connect so that a triangle is formed. If the height is greater than this side A, then there's going to be no triangle because it's not long enough to reach the third side. If your A value equals the height, then you're going to have a single right triangle because, again, that's the shortest possible distance to connect and make a triangle with three sides connecting, and that height always makes a right angle. The tricky one, I think, is when your A value ends up being larger than the height. Remember, we don't know how long this bottom side is here. So it could be short or it could be real long. We don't know that information. So with side A, we have the possibility, if it's longer than the height, we could put it two different places. It could either go here, or that same length would go here and still intersect our bottom side, because like we said, we don't know how long it is. It could be this long, or it could be this long, and make this like big old triangle here. Or we could have this smaller one here. This situation is called the ambiguous case of law of sines because we don't know. It's, ambiguous. We don't have to rely on an illustration to draw the correct conclusion in the ambiguous case. We can apply the law of sines to the values of A, B, and our angle A that were given and use some basic properties of geometry and trigonometry to determine which situation applies. You should keep the following things in mind. For any angle theta of a triangle, sine of theta has to fall between 0 and 1. Remember that sine has to be between -1 and +1, but because we're dealing with a triangle, negative numbers don't make sense for the context, so sine has to be between 0 and 1. If sine is exactly 1, then theta is 90 degrees and a right triangle is formed. Remember that sine of theta and sine of 180 minus theta are equal to each other. We do this all the time with like our sister triangle when we're finding those. It's like, okay, sine has a 32-degree reference angle, so the sister triangle is over here, 32 degrees, but to get the actual angle measure, we subtract it from 180. So we can say that supplementary angles have the same sine value. We're actually going to use this one a lot. And the smallest angle is opposite the shortest side. The largest angle is opposite the longest side. The middle value angle is opposite the middle side. So we're going to use this one a lot too. When I'm doing this, I don't actually calculate the H value. I know a lot of instructors will say, oh, let's figure out the H value and then we'll know if we have 0, 1, or 2 triangles. Personally, I just do every problem as if I had 2 triangles, and if I don't have 2 triangles, it will clearly present itself that there are not 2 triangles. So we want to solve the triangle, which is the same as saying determine the remaining sides and angles of each triangle. We'll round each answer to the nearest tenth. I see a known pair, so that tells me law of sines right away. But I only see one angle, so this tells me it might be the ambiguous case. I'm going to have to watch out. But I'm going to start it like normal. Law of sines says that A over sine of A is going to be equal to C over sine of C. And we're going to solve for angle C. We'll cross multiply. Then we need to isolate the sine of C so we can use our inverse sine. We'll do that by dividing. And then to get our C, we'll have to do inverse sine. And we'll put it into our calculator. Now, I know you guys aren't really into talking today, but I would really appreciate if you guys gave me values so that we can reach these conclusions about whether we have 0, 1, or 2 triangles together rather than me just telling you. I think it's going to be more meaningful if you're seeing the numbers in the calculator that tell us what's going on with this. So if somebody could give me my C value.
I got 27.59, but I'm not sure if that's right.
That sounds good to me. And then we're rounding to the nearest tenth, so I'm going to make it 0.6. Any questions on what's happened so far? We've just done law of sines like we did last week. Well, as I said before, I always assume that there are 2 triangles, and if there aren't 2, it'll clearly present itself. So if we got C equals 27.6, I'm saying that that's going to be my C value, my angle C for triangle 1. To get our C value for triangle 2, we're going to use this property number 2 up here. that sine of theta equals sine of 180 degrees minus theta. And the way we're going to use that is way less complicated than that looks. So the C for our second triangle, and I'm actually going to use subscripts to indicate triangle 1 and triangle 2. The C for our second triangle is just going to be the supplement of the C from our first triangle. So this is always going to be 180 minus C1. So that's going to make our C2. What do we get there?
One 152.4.
152.4.
Okay, great. All right, so right now everything's looking good. I'm getting angles that are just like normal numbers, nothing weird's happening. So I'm going to keep running with there being two triangles. All right, what else do I have left to find? I have to find angle B and side B. Well, I always like to do the easy stuff first. So let's find angle B next. So looking at triangle number 1, how do we find our angle B? Well, we know all the angles add up to be 180, so to get angle B, we're just going to take 180 minus our angle A minus our angle C, and that should give us our angle B. You'll notice that the angle A doesn't have a subscript on it because that was given to us, so there's no possibility of that varying. That's just what it is. So what do we get for B1 here?
$108.9 degrees.
All right, let's do the same thing for our second triangle. So to find B2, I'm going to take that 180 degrees minus A minus C2. So what do we get for B2?
I got negative 15.9.
Did anybody else get that?
Yeah, I got that.
Can the interior angle of a triangle have a negative angle measure?
No.
No. So because of this negative, I know that this second triangle is not a possibility. So that's the, it will clearly present itself if there's not a second triangle. There it happened. And you'll get way faster at that. I know you're like, why didn't I just find H equals B sine of A? But you'll get way faster at doing that. And I think it's easier than having to remember another formula. All right, now that we've established there's only one triangle, I still have to finish solving the triangle. Finding side B is left. Oh, we can just use law of sines again. I'm going to start with my known pair that was given. It's 1/2 of my proportion, and then the other side B will be over sine of what we got for side B. If you want to continue with the subscript, that's fine, or you can end up getting rid of all the subscripts because there was not a second triangle. To solve for B, all we need to do is multiply both sides by sine of 108.9. We get B to be 10.7 times sine of 108.9 all over sine of 43.5. Plugging that into our calculator, we get 14.71 inches. Questions? All right, let's try another one. Oh, I see a known pair, so that tells me law of sines, and I see that I'm only given one angle, so that tells me this could be the ambiguous case. I might have two. Well, it is the ambiguous case because I don't know if I have 0, 1, or 2 triangles. But we'll start it off like normal. And then I'll assume there's 2 triangles, just like I did in the last one. And if there's not, it'll clearly present itself with a negative angle. All right, setting up here, this is going to be 1 over sine of 50 degrees. So we're using our known pair equals our side A, which is 2 over sine of A. To solve for A, we'll cross multiply. And we'll use the inverse function to get A all by itself. So A is going to be sine inverse of 2 sine of 50 degrees. So what do we get when we plug that into our calculator? Anybody get an answer? I want the answer you're getting. I know what it is. And be confident with that answer.
I got a domain error.
Anybody else get error?
Yes.
Yes. Error. This means if you get an error right out of the gates, as soon as you're trying to find the first angle, this means that the side's too short. It never touches. There's no triangle here. So you're second guessing yourself because you got an error. Now, of course, after I got an error one time, I'd do it a second time to make sure that I didn't make an error. But after that, you should be confident with it. Questions at all? Okay, let's try another. I have a pair of A's, so I know I'm going to use law of sines, but I only have one angle, so that tells me that's the ambiguous case. I'm going to start it like I always do. So 6 over sine of 35 is going to be equal to my side B, which is 8 over sine of angle B. I'm going to start by solving for B. Cross multiply. Divide by 6. You could simplify that 8/6 if you wanted to. I probably wouldn't, just because I know I'm going to plug it in my calculator anyways. And then we'll use our inverse sine to find angle B. Do we get an error this time?
I got 49.9.
what was it, 49.9?
Yeah.
All right, 49.9. So this means that a triangle does exist because I did get an answer. Now I'm not sure if it's one or two triangles, so I'm going to proceed assuming that there are two triangles. For triangle 1, our angle B is equal to 49.91. And by the way, if you get a B that is not negative, like your first angle is not negative, you're absolutely going to get one triangle. Now we're just debating between whether we have one or two triangles. How's my audio? Is it bad?
No, it's doing well.
Okay. After this class is over, I'll shut down all my video making stuff behind the scenes. All right, so B1 is 49.9. So B2, our second option, is going to be the supplement of that. So the supplement is 130.1. And I'm good with this second triangle as long as I don't get a negative angle measure. All right, let's find the next angle in each triangle, which is going to be C1. Remember, to find this, we're taking the total 180 minus the angle that was given minus the angle we found. And I know this is going to exist because I'm guaranteed a first triangle. So C1, 95.1. Let's check in the second triangle. And the reason I do the angles, by the way, before I do the sides is because, first off, the angles are way easier to find than the sides. I don't have to do much work. And secondly, it's the angle that's going to be negative that tells me that there's not a second triangle. So why do all the work of finding the side first, only to, after the fact, be told there's no triangle? To find C2, we're going to take our 180 minus the angle we were given minus the angle we found. So this time, what do we get for C2? Because this is the critical point. If we get a positive, we know there's a second triangle. If we get a negative, we know there's only one triangle.
I got 14.9.
Anybody else get that? Since we got a positive number there, we know for sure there is a second triangle. So now we have to find our side C for both triangles. You're getting feedback now, Amber, or was that earlier? Okay, so let's find our side C's for both triangle. Start with my first triangle. Side C, I'm going to start with my A pair, just like I did before. So that's a 6 over sine of 35 is going to be equal to our side C1. Here, the subscripts are necessary because we have the two different triangles to keep track of. Over sine of 95.1. To solve for C1, we'll just multiply both sides by sine of 95. And we get C1 to be 10.4, and our unit is yards. And then we'll do the same exact thing for our second side C. 6 over sine of 35 is equal to C2 over sine of 14.9. Multiplying both sides by sine of 14.9, we isolate C2. And then we want to plug that into our calculator. 2.69 yards. Ambiguous case? Definitely on the test. There'll probably be multiple questions on that next test involving the ambiguous case of law of sines. Oh, sorry, this should be 2.7 from rounding to the nearest tenth. Questions, anybody?
I'm just like having a hard time like visualizing it. Like when we're talking about like different triangles and stuff, like I don't.
Okay. When we're in class, I bring like sticks and stuff. I do it with sticks. Okay, so say I know that this is 6 long, and I know that, Jesus. All right, I don't feel like that's a good choice. Sorry, I gotta do this again. This needs to be longer. Oh, here, hell, I'll just do the 6 and the 8. This will be perfect. All right, so if this is 8, I want to draw this just like this example here. That's 8. We know that the other side is 6. And we know angle A, which is this angle down here on the ground, is 35 degrees. Now, if I did straight SOHCAHTOA here to find out the height, I would say that sine of 35 is equal to h over 8, so h is equal to 8 sine of 35. Now, I don't know what this is, so I need you to pop that in your calculator. It's going to be less than 6, but I don't know what it is. Jordan, did you put that in your calculator?
Yes, I got 4.588.
Okay, 4.58. Just want to show that we're getting something less than 6, which is the other side. And the other side, so because this other side is longer than the height, it can't be just straight down because the height is what's straight down. So this other side has to be like at a diagonal. And we don't know how long the bottom side is. So this 6 could be over here, or it could be over here to complete the triangle, and it wouldn't affect these two things that are known, right? Because the only other thing we know is the length of this other side, the red side, 6, but I don't know how it's positioned. It could be positioned so that we got an acute triangle. It could be positioned so that we get an obtuse triangle. And we just don't know which one it is because we weren't given enough information to distinguish between the two. So that's why we have to give an option for triangle 1 and an option for triangle 2. Did that clarify it at all?
Yes, thank you.
And that's why all the other answers trickled down and was different. So say this is our angle B here. When we got the big number for angle B, side C is the one on the bottom. That's why we got such a small answer for side C, because that side of the triangle was positioned so close to the other one to get that big obtuse angle B. And that's why in the other one, when we got the smaller angle for angle B, the acute one, we ended up getting a bigger number for side C because the distance, it had to be pushed way over to the side. Anybody else? Questions? All right, let's take a look at an application problem. After a windstorm, you notice that your 16-foot flagpole may be leaning, but you're not sure. From a point on the ground 15 feet from the base of the flagpole, you find that the angle of elevation to the top is 48 degrees. We want to know, is the flagpole leaning? And if it is, we want to find the acute angle to the nearest degree that the flagpole makes with the ground. So let's start with a picture. Here's my ground. I have my flagpole that may or may not be leaning. From standing 15 feet away, so I'm gonna go 15 feet this way. The angle of elevation to the top of the flagpole is 48 degrees. And I also know that my flagpole is 16. And we want to figure out if is the flagpole leaning. How would we determine if it was leaning?
Would you try to find the angle at the top and then using like what we have, and then depending on if that bottom one's a 90-degree angle or not, we could tell if it's leaning.
Right. So ultimately, we need to figure out what this angle measure is down here. I'll call it theta. Right? Because if it's 90, then we know it's straight. If it's anything other than 90, we know it's leaning. But as Jordan mentioned, we can't go directly to that. There's no way to directly figure out what theta is. We have a known pair right here. So that tells me law of sines, but the only other thing I was given was 15, and there's nothing across from the 15. So I'm first going to have to find that angle up at the top. I'll call it alpha. And then we'll use the fact that the sum of the interior angles of a triangle equal 180 to figure out that theta at the bottom. All right, so we're using sine. Our known pair, this is going to be 16 over sine of 48 equals 15 over sine of alpha. Solving for alpha, we'll cross multiply. Divide by 16. And then we'll use our inverse sine. We get alpha to be 44.16 degrees. Questions on anything we've done? All right, let's determine if it's leaning now then. So theta is going to be 180 minus 48 minus 44.16. That gives us theta being equal to, what's that, 87.84. So is it leaning?
Yes.
Sure is. But then there was a second question. If it is leaning, we want to find the acute angle to the nearest degree that the flagpole makes with the ground. So this is an acute angle, because like if we had measured from over here, this one would have been obtuse, so we would have had to find the other one. Because when you set up your diagram, you may have it set up from the wrong side. All right, it's leaning because it's not 90 degrees. We found the acute angle, but they asked us to round to the nearest degree. So 88 degrees is our final answer. Questions, anybody? All right, then we will move on to the law of cosines. This handles our case 3 and our case 4. But again, I never think of the cases. If I got a known pair, it's law of sines. If I don't have a known pair, it's law of cosines. But I'm going to start by deriving law of cosines for you, just so you understand where it comes from. I'm going to start with an oblique triangle, ABC. I'm going to choose a coordinate system, x, y, put my axes so that the vertex B is at the origin and side BC is along the positive x-axis. If we let xy be the coordinate of vertex A up here, then the following things are true for angle B. So what we did from our point A is we dropped a perpendicular down to the x-axis, creating a 90-degree angle. So there's our angle B. Using SOHCAHTOA, since we have a right triangle, we can say that sine of B is y over c. And if we look at so we can then solve for y and then get y equals c over b. Then we can say that cosine of angle B, adjacent over hypotenuse, is going to be x over c. We can solve for x and get x to be c times cosine of b. So that ordered pair can be changed from x comma y to c cosine of b comma c sine of b. All right, great. Point C over here has the coordinates a comma 0. So we're using a because that's opposite our angle A, and then the y coordinate is 0. So we can say that line segment that has length b and point A has the coordinate c cosine of b, c sine of b. Well, I'm going to use distance formula to figure out what side B is. And our distance formula is just that the distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Same distance formula we've always used for calculating distance between 2 points. So it turns out that b is equal to c cosine of b minus a squared plus c sine of b minus 0 squared. And we want to simplify. So this right here, you're going to have to write twice and multiply out. When we do that, it becomes c squared cosine squared b minus 2ac cosine of b plus a squared. And now here, c sine of b minus 0, that minus 0 just is gone. So really it's just c squared sine of b squared. All right, I'm just going to do some rearranging. I want to move this towards the front. So this is going to be c squared cosine squared b plus c squared sine squared b minus 2ac cosine of b plus a squared. Out of those first two terms, I can factor out a c squared, leaving us with cosine squared plus sine squared. And we're always happy to see cosine squared plus sine squared because using our Pythagorean identity, it turns into just 1. So b is going to be equal to, I'm going to do a little rearranging again, c squared plus a squared minus 2ac cosine of b. So that's the distance of b. I'm going to square both sides. And we get that b squared is equal to c squared plus a squared minus 2ac times cosine of b. And that right there is our law of cosines. I just wanted to show you the derivation where it just really comes from distance formula for us. This result is one of 3 possible forms of the law of cosines. In our work, we could have just as easily placed vertex A or C at the origin, right? If we just rearranged the variables, we would have got different variables in our algebra there. So law of cosines can be written out 3 different ways. Now, I don't want to remember 3 different formulas, so I always think of this as the same formula, and I remember it more so in words. I'm like, all right. Now, there's not going to be a known pair, so you kind of got to start with the angle because there's only going to be one angle. So we need to know where that goes. The side that's opposite the angle we're dealing with goes first. So it's the first side squared equals the other 2 sides squared and added together minus 2 times those sides times cosine of the first side. I don't know. That's how I remember it because I'm not trying to remember 3 formulas. Just it follows that pattern. Law of cosines is great because there is no ambiguous case. Yes, it's a lot to plug in your calculator, but it always works out nice. We want to solve the triangle and round to the nearest hundredth. You'll notice here they don't give us any angle measures, so we can start with whatever side we want. We just know that if we start with side A, we're going to be finding angle A first. So I'm going to start with side A first. It's going to be 4 squared equals 3 squared plus 6 squared minus 2 times 3 times 6 times cosine of A. And we need to solve for A. I think I'll multiply out all the numbers we know. So this is 16, 9, 36 minus 36 cosine of A. 16 equals 45 minus 36 cosine of A. We want to isolate the cosine, so let's subtract 45 and divide. We get 29 over 36 equals cosine of A. And lastly, to find A, we're doing an inverse of this 29 over 36.
Wouldn't the 29 over 36 stay negative?
Nope, because we're dividing both sides by a negative.
Oh, okay, never mind.
Always good to double check our signs, though. And we're rounding to the nearest hundredth. We get A to be equal to 36.34 degrees. So there's angle A. We want to do this a second time to get one of the other angles. I'd do angle B next, and then we'll be able to get angle C easily, knowing that the three angles have to add up to be 180. And we do have a known pair at this point, so you could do law of sines if you wanted to, but I don't want to have to deal with the ambiguous case. Since only one angle is known, I don't want to have to double check that. Is there two triangle stuff? So I would just do law of cosines again. This time I'm going to put side B first. So b squared equals a squared plus c squared minus 2 times a times c. See, it's so hard for me to even remember the variables. So it's one side squared equals the other two sides squared and added together minus 2 times the sides on that same side, and then cosine of the first side, which is b. And we solve for b. Subtracting the 52 over, that's going to be negative 43. Dividing both sides by negative 48, which is our left side, positive. So angle B is going to be cosine inverse of 43 over 48. Rounding to the nearest thousandth, we're going to get 26.38 degrees. Questions at all? Well, then to find angle C, we're just going to take 180 minus angle A minus angle B, and that'll give us our angle C. And we get angle C, 117.38.
Isn't it 2/8?
Yes, it is. There we go. Questions, anybody, on the law of cosines? On Thursday, we'll look at a couple applications involving the law of cosines. We'll learn a third way of calculating the area of a triangle, and then we're going to move on to vectors.
Okay.
All right, everyone have a wonderful day. I will see you on Thursday.